Hello, everyone. The starting point is prologue. I guess everybody knows prologue. Anybody who does not know prologue. Does not know prologue. Okay. Well, actually, prologue may not be a successful language commercially, but it is successful in producing offsprings, yeah, and also influencing other languages. Okay, 2 days ago, Michael Kiefer presented a tutorial on Eagle, and which is an offspring of prologue, yeah, which was designed for knowledge representation. And Picat is another offspring of prologue, which was designed for scripting and modeling, yeah. Well, to this audience, I should say it is designed for rule-based enterprise optimization. Well, so this actually a couple of months ago, I gave a tutorial at a conference called Flops. It is the same tutorial, and actually this tutorial is available on YouTube. So, but of course, I don't want to just play the video, here. So I want to do some, present the same tutorial in different way, yeah. So I'm going to spend some time showing you a demo, okay. So this presentation includes contributions from several people who have been working on this Picat language. Well, some of them, okay, from the very beginning. Okay. So what is Picat? Okay, Picat is designed for scripting and modeling. Okay, many of you know, okay, Python. Python is a wonderful language for scripting. Okay, so, and Picat is as good as Python for scripting. And it is also good for modeling, yeah, for solving combinatorial search problems. Okay, so the name, okay, is an acronym. All right, so each letter stands for something. Okay, P for pattern matching, and all predicates functions are defined using pattern matching rules. I for intuitive programming. Okay, so intuitive means, well, you have a computation and you can describe it naturally, yeah, in Picat. C for constraints. It supports constraint programming. Okay, actually, it provides an interface to several solver modules, including CP, set, satisfiability, and MIP, mixed entity programming solvers. And A for actors, all right? So I'm not going to talk about actors. Okay, so actors, for example, the CP solver uses actors. Okay, so a propagator, constraint propagator is an actor. Okay, it's event-driven, yeah? And T for tabling. All right, so well, this is good for dynamic programming solutions. This language is built upon logic programming concepts, including unification, logic variables, and non-determinism. Okay, so but this language provides these concepts in a different way from prologue. Okay, so for example, non-determinism. Okay, it requires called a unification. It supports unification, but it requires unification to be used explicitly, and the same for non-determinism. Okay, and it provides supports language constructs for scripting. Okay, including functions, loops, list, and array comprehensions, and also assignments. Yeah, amazingly. Okay, it supports assignments. Yeah, and it provides facilities for solving combinatorial search problems. Okay, including tabling for dynamic programming, and several solver modules, and also a planner module. Okay, for planning problems, which is implemented by using tabling. All right, so this is outline, but I don't think I'm going to finish it, finish everything, because, well, this language is a very simple language. I guess Paul knows it. Okay, that's why he gave me 1 hour and give Michael 2 hours, you know, so. Well, just first let me talk about the basics. Okay, data types is a dynamically typed language. Okay, all the data types are from Prolog except for arrays and maps. All right, so each type provides, you know, certain built-ins. Yeah. Okay, variables. The syntax is also from Prolog. Yeah, each variable name begins with a capital letter or an underscore. And, well, I'll show you later on in a demo. Atoms and characters. Okay, these are names, constant names, symbols, and numbers. Okay, numbers in Picat are not that different from numbers in other languages. And lists, yeah, okay. So, and strings. A string is a list of characters, okay. And structures. Well, again, same as in Prolog. Okay, there is one exception because this language supports functions. Okay, in order to write a structure, you have to precede it with the $sign. So the compiler knows, oh, it is a piece of data, not a function call. And arrays, yeah, arrays, again, it's a special kind of a structure. You just put these elements in a pair of braces. And, okay, so maps and sets, again, nothing is new. Okay, you can use the index notation to access compound arguments of compound values. Well, and you can use list comprehension to create lists, and you can also use OOP notation to chain function calls. Okay, so these are the unification. You know. Okay, so let me show you. So the system is, okay, actually there is nothing to install. You just download the system, okay? So, and make sure the executable is in the path, and then just type it, and then you're ready to go.
I don't think they are showing.
Oh, that's interesting. Why?
Let's see if you switched by mistake to extended screen. We move the mouse, and yes, it's extended screen because I can see the mouse now. So let's do this and change to duplicate.
Mm-hmm.
Now we see your screen.
Cool, cool. Okay. Well, so this is the Picat interpreter. Okay, you can type commands. Okay, X. Okay, X is 1. All right. So, and for each type, you can check the type. Yeah. So you say okay, var X. Yeah. So semi-Prolog, yeah, and a list. All right, you can create a list. Okay, so A, B, C. All right, so you can also create a list using this new list. All right, create a list of say 10 elements. All right, and you can use this index notation to access, access a list. Yeah, so for example, A, B, C, and then you say print, okay, X, say 2. All right, so, oh, well, you see B, yeah, B is printed. Okay, you can use list comprehension. Let's say, okay, A is, this is a range, say, from 1 to 10. Okay, you get a list. Let's say step 2. All right, you get this list. You can use the list comprehension to do it. So X, what is X? X is in 1 to 10. Okay, you get a same list. Yeah, it's called a list comprehension. All right, you can do this. Okay, I give some property. Okay, X must be even. All right, see. All right. So arrays. Okay, similar. So what do you do? Okay, here you use braces instead of brackets. So it is an array, yeah? It is an array. Okay, arrays provide constant time access, unlike lists, because a list is a linked list. Okay, structures. Oh, you can also have array comprehension. Okay, array comprehension is, okay, just do this. Yeah, it gives you an array, not a list. And the structures, X is, for example, Stony Brook. Okay, Stony Brook, what else? Great University, and Wales population. Number of students, 20,000. But don't trust this number. Okay, so, and you need to proceed with the $sign. Otherwise, the system will say, oh, it is a function call. It's calling a function, okay, with this name SB, yeah? Okay, and anything else? Maps. Okay, you can create a map. Okay, new map. New map. Okay, you can create an empty new map, and then you can put something. Okay, put something. Let's say A is mapped to 1, yeah? And okay, B is mapped to 2, yeah? Okay, you can do that. Okay, and you can use get. Get is a function, yeah? Is a function, so get. All right, so get, let's say Y. I use get, the value associated with the key A. All right, so what happens if the key, there is no such a key, you get an exception, yeah? Key not exist, okay, because it's a function, okay, it doesn't fail. Okay, in Java, you use get. If there is no such a pair, then you get a null point. Yeah, in here, there is no null point, so what do you get? You get exception. So you could do this, get, okay, so if C is not there, then you can specify a default value. Okay, let's say 3. Okay, if get C, if there is no pair with this key C, you get the default value. Okay, then instead of getting an exception, you get a default value. All right, new set, you can create a set. All right, basically a set is a map. Okay, so a set of keys. Okay, no values. Okay, so these are the basic types. Okay, very simple language. Okay. All right, so well, it supports non-determinism. Okay, so well, only a few built-ins are non-deterministic. For example, this member. Okay, you can use this to retrieve elements from a list one by one through backtracking. Yeah, between is another one. Yeah, and well, same as in Prolog, you can use once. Okay, to control backtracking. If you only need one solution, use once. Okay, it supports high order calls. Okay, predicate calls, function calls. Okay, and it also have global maps. Well, as you see in the previous demo, okay, each query, okay, the system doesn't store the result, unlike in Python. Okay, in Python, all the results are stored. Yeah, in here it doesn't store any result. So each time you start a new command, okay, you start a new session. Yeah. Okay, unless you use global maps. If you use global maps, then you can store results in the global maps, and then later on you can retrieve data, okay, from the global maps. There are 3 types of maps: global heap map. Okay, depending on where you store the data. Okay, you store it on the heap, then it's heap map. Store it on the global map, it's global area. Okay, store it in the table area. And there are several modules. These modules are pre-imported, I/O, math, okay, utility modules, okay, statements. These statements, again, are from Prolog. Most of them are from Prolog, okay? Except you use if, then, else, yeah? Exceptions, again, okay, very similar. And it provides, suppose, loops, yeah, for each loop. Okay, so this one is... well, for each, we call iterators, yeah, iterators. This EI in DI is called an iterator. So just for each combination of values in these domains, okay, if the conditions are true, then you execute this goal. That has very simple semantics, okay. But there's a naming scope, okay, so it has well, some variables are global and some variables are local. Okay, so Picat uses a very simple scoping rule, okay, which says variables that occur within a loop but not before in its outer scope are local to each iteration. So, for example, we have this, yeah? We have an array A, and then we say for each I, and then we assign this one to X, okay? And then you see X doesn't occur before in the loop, so X is treated as a local variable. That means for each iteration, X is a new variable. So that's why you see different variables here. All right, in this example, X occurs before in the loop. Okay, then you see X is treated as global. Then all iterations, okay, share the same variable. Yeah, so you create a list of X's, the same variable X's. Okay. It also supports assignments. There are two types of assignments. Okay, one is this one destructively updates a component of a compound value, okay, using this. And the other type of assignment is the left-hand side is a variable, okay. This one is basically the compiler introduces a new variable, okay. And after that, it replaces all occurrences of this variable, okay, by this new variable. Okay, so for example, for this query, okay, you begin with X being 0, and then you assign X plus 1 to X. Okay, then the compiler introduces a new variable. And after that, all X's are replaced by this new variable X1. Okay, so this one is you don't need to invent new variables. You can use the same variable to store values, at different stages during computation. It's very convenient. Okay, so since we have assignments, then we can have while loops. All right, so Picat supports it's a multi-paradigm language. It supports logic programming, functional programming, and scripting. So for logic programming, okay, so you can define predicates. There are two types of rules. One is called non-backtrackable or deterministic rule, and the other one is non-deterministic rule. So backtrackable. Okay, for example, this member can be defined, okay, this way. So this one question mark arrow means you rewrite this code, okay, into the right-hand side. This question mark arrow means, this rewriting is not a commitment. All right, I just try it, and if in case, okay, it fails, I backtrack, yeah? And this arrow, that means, okay, this is a commitment, yeah? Okay, don't backtrack. Okay, this is very much different from Prolog. Yeah, Prolog, by default, every rule is backtrackable. Okay, in order to make it stop backtracking, you use cut. Yeah. Okay, so it's called explicit non-determinism. Okay, and it also unification is all these rules are pattern matching rules. Okay, pattern matching rules, unlike in Prolog, all clauses are unification based. Okay, so a call matches this head. Okay, matches this head if you can find the bindings for these variables. Okay, to make the call and this instance identical. Yeah. So pattern matching is used. So after pattern matching, the code doesn't change at all. Yeah. Okay. This one can the head of the goal may change, but the code doesn't change. And predicate calls, okay, of course, for predicate facts, it's tedious to to write them as rules. Okay, so just as syntax sugar, okay, you can write the bunch of facts and then tell the system how the facts are indexed. Okay. And functions, well, you can write functions in a similar way as you do in functional programming language, as in Haskell, F#. And a function rule, okay, takes this form. So head equals the written expression. Yeah. and then condition, and then body. It's like in function you say where, all right? So this is the equation, and then you say where. This condition, if the condition is true, then you write this equation, okay, to the right-hand side. All right, if the condition and the body are true, yeah, empty, okay, then you can just omit them, yeah? So, for example, this Fibonacci function, you can define it this way, yeah? Just as a bunch of equations, yeah? And this power set, okay, so using equation and this compression, it is pretty convenient to describe. Okay, this quick sort, okay, can be defined in several lines. So, of course, there are big differences. As a function program language, there are big differences between Picat and a language such as Haskell. Yeah, first, it is dynamically typed, so types are checked at runtime. Okay, and also it is a strict language. That means all arguments are evaluated before, calls are made, and it supports high order functions, but high order functions incur high overhead. So using high order functions is not encouraged. So what I normally do, I use list comprehension instead of high order functions. So patterns. Okay, in pattern matching, okay, you have pattern matching rules, and you can use well, as in Haskell, you can have called as pattern. Okay, so you pattern matching. Okay, after the pattern matching is successful, all right, you can use a variable to reference, okay, the term that matched this pattern. Okay, and in the body you can use it to reference the term. So in this way, you don't need to create the term again. Well, this is an example. So scripting example. So to draw this Pascal's triangle, okay, this one with loops, you can write it in a procedural way, yeah. This is another example. Okay, so giving a directory, you want to traverse the directory, yeah. So let's say giving a directory, what do you do? Oh, you need to import OS, the OS module. What do? You get all the files, and for each file, okay, and if file is not a current file, is not the parent directory, what do? You get the full name, and then you check. If it's a directory, then you go down. Otherwise, you print out the name. Okay, it's very simple. Okay, actually, this for each loop makes the description very concise. All right, so here are several examples. Okay, so let's say write a function that returns the number of zeros in a given simple list of numbers. Yeah. All right, so you can, of course, you can write a function or you can write a predicate. Okay, actually, there's a more convenient way to do it. All right, so count zeros, you can just do this using a list comprehension sum 1 for each zero in this list, sum 1. Then it gives you the number of zeros in the list. And then the compiler compiles this into a program, okay, that looks like this. Well, you can see, okay, you don't pay a price for this, okay. It's very efficient. All right, the system doesn't build a list, of ones, and then counts the ones. Okay, so okay, and here's another exercise from, I think this exercise is from 99 Lisp problems. Yeah. All right, replicate the elements of a list a given number of times. Okay, so for example, you replicate this list A, B, and 3 times. Then you get an A, 3 A's, and 3 B's. Okay, so what you can do, you can just do this. Yeah. So replicate, okay, list n times. So what do? X. Okay, so for each x in L, and then I do n times. Yeah, this variable is not important. So you use an anonymous variable. Okay, so then you get it. Okay. Well, this is an example from Google CodeGem. Actually, if you go to the Picat's website, you will see a link to the Google CodeGem page, and you will find a lot of Google CodeGem solutions. This is a practice problem. So giving a list, this one a string, giving a string. This is the number of test cases. So what you want to do, you just reverse a list, yeah? So say this is a test, and you reverse the list, okay? We can do it in Picat this way. What you do is, okay, read line and then 2 int. You converted it. Read line returns a string, and you convert it into integer, number of cases, and for each test case, what do? You read a line and a split. This split gives you a tokens, list of tokens. And then what do? You just print it out, yeah? And then reverse, because you want to reverse the tokens. Okay, that's it, okay? Here's another example called store credit. Okay, store credit. Okay, you take a look at this. Giving an integer C, which is a predicate, and a sequence of integers. Find the indexes of the 2 items that sum up to C. Okay, this is okay. So for example, in here there are 2 test cases. Okay, so this is integer. All right. So this is the 3 items. Okay, you want to find 2 items that sum up to 100. Okay, so well, you already know the answer, yeah. So this one and this one sum up to 100. Okay, so we can do it in Picat easily this way. So read the integer. All right, and then for each test case, you read the credit, and then you read the number of items, and then okay, you also read number of items and read the items, and then what do? You do generate and test, yeah. So first generate one index I, and then generate another index j. Okay, and then okay, so if these 2 items sum up to the credit, then you print out the result. Okay, of course, this is not that efficient because it takes in square time. Okay, you can use a map, okay, and make it linear. Okay, so I'm not going to, yeah.
So do you have constraints in Picat?
Sure, I'm talking weight.
Okay.
I
so
talk about
you can only define a constraint.
I talk about that later, yeah. Okay. So this is, yeah, here you are. That's the second part. So constraint programming. Okay. So Picat provides a common interface, okay, to several constraint solvers, the CP solver, the set solver, and the MIP solver. It's a common interface, so you can switch from one solver to another solver seamlessly, yeah? Okay, the interface allows you to declare domain variables or decision variables and write constraints. So arithmetic constraints, Boolean constraints, table constraints, and global constraints. So in order to solve a problem, what do? You just call solve. That's it, yeah? And here's an example. Okay, this is a famous example. Yeah, send more money. Okay, you create the variables and then give the constraints and then call solve. Okay, in this example, okay, I used import CP. Let's say, all right, CP doesn't work, okay, for this problem. Then you can try a different solver. So you just change it, import set. All right, so instead of using CP, and then you use a set solver, yeah? Okay, and here's another example. Actually, this loops and list comprehensions, okay, make this language very convenient as a modern language. Yeah, you can describe constraints using loops, yeah? So this is pseudo puzzle. Okay, you could do it. Try to describe this in Prolog. You feel pain in the neck. It's too much work. Yeah, why? Because Prolog doesn't have loops. All right, using Picat is so convenient. Yeah, you just say each row, every row, okay, is different, and every column is different, and each of these small squares, okay, also have different numbers. That's it. Okay, here is another puzzle called a number link. Number link, well, giving several pairs of numbers, 1, 1, 2, 2, 3, 3. Okay, so what you want to do is you want to find paths to connect these pairs of numbers. Yeah. Okay, again, so you can use this to describe these constraints. Okay, easily. So here is an instance. Okay, it is a very hard instance. Okay, which is contains about 50 pairs of numbers, and you want to find a path to connect these numbers. Actually, this instance was submitted to an ASP competition, but this one was not used because it was so hard, and no solvers could solve it. Okay, so and Picat could solve it in 150 seconds. Actually, on a slow computer, not this fast computer. Okay. So here's another. For certain problems, actually this this one uses set solver. Okay, actually the set solver, the performance has improved dramatically. 2 years ago, I gave a talk at ICOP, and at that time, I compared SAT and CP on the benchmarks used in the Mini-Zinc Challenge 2013. And SAT solver, at that time, the SAT solver was a very simple, compiler, compiles constraints down to conjective normal form, and solved 63 instances, and the CP solver solved 62 instances out of 100. And now the current version, actually we submitted another version yesterday, and the latest version, could solve 90 out of 100 instances. So it has drastically improved the performance. Okay. So for certain problems, all right. So MIP is still your choice. Yeah, MIP has longest history. Yeah. Okay. So for example, for this max flow problem, MIP is unbeatable by other solvers. SET doesn't work, CP doesn't work, but MIP can solve graphs of hundreds of nodes easily. Yeah. So that's constraint programming modules, and the next one is dynamic programming. Okay, so many systems support tabling, and tabling is a nice thing for dynamic programming solutions, such as XSB. Yeah, so Eagle with tabling is a key technology that underpins the Eagle language, as far as I understand. So the idea is very simple. Yeah. So you have a call and you compute it. The first time you compute it. Okay. Second time if you see the same call, you don't compute it. What you do is, you just look up the table and grasp the result. Yeah. So a simple example is this Fibonacci function. Okay. It takes exponential time to compute. If you table it, then the complexity drops to linear. Okay. So here is another example. You compute a binomial coefficient. This is a recurrence relation. And of course, if you don't, actually this is an interview question. This is one of the interview questions used by Google. Yeah. So let's say, because of overflow. Yeah. Let's say we have a formula. We have a formula for this binomial coefficient. Yeah, it is. Everybody knows it. But if you use that formula, it overflows. Yeah, overflows. Yeah, because you need to compute a large numerator and then compute a denominator and then divide the numerator by the denominator. Yeah. Okay. So the question is, how can you compute this binomial coefficient without, overflow? Yeah. Okay, this is the solution. You use this binomial coefficient. The question is, if you use it, it's very slow. It takes exponential time to compute. Yeah. So what you can do? You can just table it. Yeah, you can table it, and now good. It doesn't overflow, and it's very quick. Yeah. Well, in general, this dynamic programming is this tabling is good for optimization problems. Yeah, for example, for path finding, shortest path problem. Okay, for path finding problem. Okay, so let's say you have a state. Okay, you want to find a plane. Okay, of the shortest of the slow minimum cost. So what do? If the state is already final state, then you are done. Yeah, you just return an empty plane. Otherwise, what do? You take an action. Okay, to transform the state into another state, and then keep going. Yeah, keep going. So this is well, using tabling, it works nicely. Yeah, for finding planning problems. So, well, since this one is nice, I mean, for path finding problems, it's very nice. And we introduced a module for planning. All right, so you don't need to use tabling. Okay, you can describe planning problems without using tabling explicitly. Yeah, so if you use this planner, what do you need to do is you just need to describe two things. First, define a predicate named final. Okay, just tell the system, okay, which state is a final state. And then you define the predicate action. Okay, so how to transform one state, okay, into another one. That's it. That's all you need to describe. And then what do you need to do? You just need to call a predicate. Okay, there are several search predicates. Best plan, or just find a plan, or okay, there are several planning strategies. Yeah, so iterative deepling, you want to use iterative deepling, or you want to use branch and bound, or you want to use unbounded search. There are several search predicates. That's it. That's all you need to do. Yeah. So here is an example for this famous this farmer's problem. Well, I think because I'm giving a tutorial at this conference, I should use this monkey and a banana problem. I remember when I was a graduate student, I played with this OPS 5, and the first example is monkey and a banana. Yeah. Okay. The goal of the monkey is to grab the banana. Yeah. And the monkey can move chair, and then can climb the chair. Yeah, that's the example. Yeah, I should have used that example. So that's a planning problem. Yeah. Okay, so you can easily describe it. A bunch of actions, and then the goal. The goal is if the monkey has a banana in the hand, that's the goal. Yeah, and then you can find the plan. All right, so here are the plan search predicates. You can say plan unbounded. Plan unbounded, this is like the tabling version. Yeah, you can keep going. Yeah, keep going. Okay, it's unbounded search. Okay, you can use or just find the best plan, or you can use a plan. Just find any plan, or use best plan, which does iterative deepling search. Or use best plan BB, means branch and bound. Oh, the idea is you find the first plan, and then you try to find a better plan. Okay, until you cannot find a better plan. That means the previous plan you found was the best plan. And you can also use heuristics. Yeah. So this function that returns the current called resource. Okay, resource. So then you can use this to determine as a heuristic, and you can use a heuristic function, okay, to determine if the current path can lead to a better plan. If it cannot, then you fail immediately. Yeah. Okay. So this is heuristic search. Well, let's take a look at this 15 puzzle example. Okay, if you want to solve this in Prolog, well, it's very slow. It's very slow. Okay. So that's why most Prolog books they use 8 puzzle, not 15 puzzle. Yeah. Mm-hmm. Well, actually, if you use this, you could try 24 puzzle. Yeah. Okay. Why? Because the planner is Okay, very efficient. So in here, what we can do is, okay, we need to first find a data structure to represent the state. Yeah, what we can do is, the initial state. Okay, so let's say the piece one. The piece one is, where is it? What is actions? Okay, that's what you need to describe. All right, so you can try it. If it doesn't work, then you can use some heuristic function. Okay, for this one, there's a famous heuristic function called Manhattan distance. Okay, so because from the goal state, from the current state to the goal state, you just compute the Manhattan distance because, okay, you need at least this number of moves in order to reach the goal state. Yeah. So what you do is, okay, you have this Manhattan. Okay, you can use this Manhattan distance, and then what do you do here? The current resource. Okay, if the current resource is greater, okay, before you proceed, okay, you have to make sure you have enough resources, okay, to get to the goal state. That's it. Okay, then this one does, something like A star search, heuristic search. Okay. Here's another example called Ricochet Robots. This game is you have a bunch of robots, and one of the robots is called a target robot. In this game, the red robot is a target robot. You want to move this robot to the target location. The red square is the target location. And in this game, okay, a robot can move, move horizontally or vertically. Okay, but the rule is once a robot starts moving, okay, it doesn't stop until it reaches an obstacle or another robot. Okay, so you have robots. Okay, of course, some other robots help the target robot, for it to reach the target square. Okay, so if you search online, and somebody at the MIT wrote a program for this, which has more than 1,000 lines of code in C, and that program is so slow, very slow. Yeah, it takes 1 hour to solve one instance. Yeah, and okay, this is our program. So we describe the state. All right, the state is okay. The target robot is spatial. So okay, so let's say the current location of the target robot, and then the target location, the current location, and then all other robots, okay? The current locations of other robots, okay? So we only have 2 rules, okay? The first rule is, we select the target robot and let it move, It can move, in 4 directions, And then this is this question mark arrow, So it's non-deterministic. And then we select another help robot, okay, and let it move. That's it. So this program is only about 10 lines of code, and it's works very well. You check. It solves the instances, 16 by 16 instances in less than 1 second. Okay, you can even make it faster by using heuristics. Okay, you can see. All right, so let's say the current state is at least 3 steps away, okay, from the final state if this condition, if the target robot is not in the same row or the same column as the target location, and the target location position has no obstacle around it, because if it doesn't have a obstacle around it, that means you have to move a target robot, to somewhere nearby in order to move the target robot to the target location, right? So then, using these heuristics, then it becomes much faster. Well, there are some modern techniques. Okay, so you need to find the data structures. Okay, good data structures to represent the states, and preferably the data structure also breaks symmetries and also facilitates term sharing. Well, because this tabling system, okay, so each ground data is tabled only once. Okay, so if you see the same ground data, and it's never duplicated, so it's called a Hashcomb thing, yeah. So you need to help the system. Okay, there are some other modern techniques. You can use control knowledge, okay, to control search. But for example, certain actions, you can make certain actions deterministic in order to reduce the search space. And you can use heuristics, okay, how to find a good heuristic function. Okay, that's, that's how to say, very important. All right, actually, Picat is still a very young language. We have, published a bunch of papers on Picat. And last year, actually, we published a book. I didn't bring a copy. It's a very thin book that focuses on constraint solving and planning using Picat. I ran very quickly, so this is another part. I'm going to skip it. And actually, I ran very fast today, so I didn't need 1 hour to finish the talk. As I said, there's a YouTube video available, and that provides more details. If you're interested in it, take a look. I think I'm ready to take questions. Thank you.
Question? Paul? So did you try it with the Rubik Cube? I saw your 15
Rubik Cube, yes, we tried it. Rubik Cube is a very challenging problem, especially if you want to solve it optimally. Yeah? We tried it. If the instance can be solved in 14 steps, good. Yeah, we can do it. But if it's beyond the 14, then it takes too long and consumes too much memory. If you don't require optimal solutions, then it's easily doable. So let's say, there are several strategies. Okay, you can solve it layer by layer. If you follow that, that means, I set this as an intermediate goal state. All right, so I first find a plan from this current state to this intermediate state, and now I treat this as an initial state, and I set another, all right, and then find a plan. Then it's easy to solve. Okay, yeah.
Did you try to combine it with inductive logic programming methods and maybe machine learning methods of other kinds? So, for instance, to approach AlphaGo for Go?
Well, that's an interesting direction. We have never thought about that. Inductive logic programming. Well, I know tabling is heavily used in inductive logic programming. So I used to work on a system called a Prism. Which can be used to for machine learning. So that one uses tabling heavily. So for Go, you find all the explanations, and then based on the explanations, you compute the probabilities, and you learn the parameters. Okay, that could be interesting. Yes.
The slide you were talking about the robots example, you had the second action non-deterministic.
Oh, yeah?
I don't understand why you guess this slide.
The second is deterministic.
The first one is...
The first one is non-deterministic. Okay, the first one, if you make it deterministic, then this is not a search problem anymore. You don't search. That means, right? And then it becomes a greedy algorithm, yeah? If it's a greedy algorithm, you just let it go, yeah? Okay, let it the first action, applicable action. Okay, you take the first applicable action. Then it is a greedy algorithm. Okay, so, yeah, for certain problems, it works, yeah? Especially for Google Code Jam. Actually, I participated in Google Code Jam this year. How many competitions? 1, 2, 3, 4. Four competitions. You can take a look. go to the website and take a look at my blog. And amazingly, Picat is so useful for some of the problems. At least in each of these competitions, I found out at least Picat is good for at least 2 of the problems, amazingly. But I didn't win, sorry, because I'm not as smart as those smart guys. If I were, I could be, I could go to the world finals. So I think Picat could give you a competitive edge because actually there is an example. I didn't show it. This is called, it's a project. You have a bunch of topics, and then some topics are real topics, and some topics are fake topics. And what do you need to do? Oh, you find the minimum number of real topics. Well, you describe it as a constraint satisfaction problem. So for each topic, you just use a Boolean variable. It's true or it's a fake or not, 0 or 1. And then you just use minimum to solve it. Yeah? I don't think the problem writers had imagined, oh, this problem could be solved using MIP, mixed integer programming. Actually, I tried it. All right, the MIP solver, the slowest solver, GOBK, solved the largest, normally the larger data sets are not easy to solve in 1 second. In 1 second, okay, MIP solved it. And there are several other problems. Some problems can be easily solved using CP, and some other problems can be solved using set. So you have to do some experiments. Yeah. Yeah.
It's the third line of both actions, cost equal 1. How do you come to those numbers for cost?
Cost, this one, okay, because the only concern here is the number of actions you want to take. Okay, this is the only concern.
Is a non-deterministic action not more expensive than a deterministic action?
No. This is considered 1 action. Okay, you let the target robot move. 1 move is considered one step. Okay, you let the help robot move. Again, 1 move is considered 1 step. So.
Are you sure that this is optimal to solve this problem?
Oh yeah, sure, it is optimal. You don't trust me, you do it. And then solve it by hand.
Then it's not real cost. It's only counting the steps, right?
Yeah, this is basically the shortest plan. Yeah. Anyway.
So, you mentioned earlier that Picat, like Ergo, is based on Prolog, and like Ergo, it also uses tabling. But there's some kinds of tabling that Picat doesn't do or does do that are different from what XSP and Ergo do. So, what's the best way to understand what those differences are? How would you describe?
Oh, the implementation is different.
Yeah, well, not so much the implementation, but just even what type of tabling it does. Does it do all?
You mean from user's perspective?
I don't know, from a researcher viewpoint.
Oh, from user's perspective, it should be the same, no? No?
I think you're doing linear tabling, right?
Yeah.
So it's different from...
I mean, that's the implementation. Users don't care about how it is implemented. Okay, I ask a query, as long as you return me the same answer, then it's the same, yeah? Of course, performance-wise, maybe they are different.
And
I know XSP.
How semantically complete or correct is negation?
Oh, negation. That's a good question. Well, this one, Picat only supports negation as a failure. No well-founded semantics.
It's not well-founded?
No. So I think in order
so
to...
that's one difference. Because it's
in order to implement well-founded semantics, then we need to change the implementation mechanism.
Right, you can probably use some of the tabling techniques that XSP uses.
We have never thought about that well-founded semantics because I don't know. Of course, I don't work on knowledge representation. That's why we didn't have the need for well-founded semantics.
Question?
2 minutes.
I have one question.
Oh, great.
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 In fact, well,
practical aspect. Do you think that all the features that this language offers can be used in the new emerging big data applications?
Big data applications.
Do you think that
in general that's challenging for logic programming systems?
Yeah,
in general that's
yeah.
challenging.
For your language, how do you think it could be useful? For example, for filtering or for feature implementation.
All right, let me throw the ball back to you. Do you think you can do it in Python?
Yeah, of course.
If yes, then the answer is yes, because we did a comparison of Python and Picat.
Okay.
Actually, for many programs, Picat is much faster than Python.
Okay.
And also the memory manager is better than Python.
Yeah.
Yeah. For example, this one stack grows automatically. The Python stack doesn't grow automatically. It is, if it is a stack overflow, it just dies. You have to set it manually. In here, no, the system does it.
Okay.
Mm-hmm.
Thank you.
Yeah.
So I think that this concludes this interesting tutorial, and we are ready for the break.
Okay. Thank you very much.